Now that I've shown you these kinds of tricks that we play when we are doing this kind of exponent math, I'll show you why it's so valuable to be able to use it. Most of the mathematical expressions that we're going to be seeing as we do chemical equilibria, and in particular solubility product equilibria, acid-base equilibria, will involve problems like this. Problems where I'll have numbers like 10 to the minus 5 times 0.1 to the 1/2. When you look at a number like this, your response shouldn't be to go running for a calculator. Rather, your response should be that what you need to do is some simple exponent math on it. So this is 10 to the minus 5 times 0.1. That's 10 to the minus 1. Get all of these numbers into exponents. So 10 to the minus 5 times 10 to the minus 1 is equal to 10 to the minus 6. And then the square root of that is simply to divide it by 2. 10 to the minus 6 divided by 2 is 10 to the minus 3. So the answer to this particular result is 10 to the minus 3. I can even take this to the point where if I want to take the log of something like 10 to the minus 12 times 10 squared, and I want to take the square root of it, I can pull that answer out pretty quickly. 10 to the minus 12 times 10 squared is 10 to the minus 10. Square root of 10 to the minus 10 is 10 to the minus 5. The log of 10 to the minus 5 is minus 5. This is the kind of math we do when we do our acid-base chemistry, when we do our solubility product chemistry, and it's the sort of thing I'm going to be expecting you to do without a calculator, because the value of using logs, especially log base 10, is that we do not have to use calculators to do exponent math. One last thing to show you before we take a look at Le Chatelier's principle is the relationship that exists between what happens when we're working the pressures of compounds and the concentrations of compounds. Are these related to each other in any way? Well, actually, that's a pretty easy thing to figure out. If I've got gases and I want to talk about them as concentrations, all I have to remember is that PV is equal to nRT. Because PV is equal to nRT, this means that P is equal to N over V. RT is equal to that concentration term times RT. So the answer to the question, is there a simple relationship between the pressures and the concentrations, and specifically the pressures written into equilibrium constants and the pressures associated, the concentrations associated with equilibrium constants? There is a relationship between these, and this relationship is found through RT. So it's pretty simple to derive the fact that Kp is equal to K of the concentrations times RT raised to the delta N. This is the expression that allows us to convert a concentration term into a pressure term. You simply take our friend RT, and it's dependent upon the difference in the number of, stoichiometrically, the number of gas molecules sitting in your system. If that number is equal to 0, then Kp is equal to Kc. But if it differs, then we have to multiply it by this correction factor of 8.3 times the temperature. To prove to you that this is a pretty straight ahead kind of calculation for us to do, let's just go ahead and take a look at this chemical reaction here of carbon monoxide and chlorine gas to make COCl2 as a gas. The equilibrium constant for this, written as concentrations, is 20. I want to know what the K value is when written as pressures. So all I have to do is use this expression here. Kp is equal to Kc times a correction factor. So Kp is equal to 20 because that's our concentration equilibrium constant. And then I have to multiply through times RT. R in this particular case, because we're working with liters, atmospheres, degrees, and moles, is 0.082, as we saw back when we were doing the ideal gas law work. There's a temperature right there. And then I need to raise that to delta N. Delta N is the change in the number of gas molecules here. And you see that change in the number of gas molecules is 1 is how it ends up, 2 is how it starts, So this is raised to the minus 1 power. So this is 20 times 0.082 times 298 to the minus 1. And the answer is that Kp is equal to 0.82. So here's a very simple mathematical expression that allows us, if you were given values as pressures and you want to turn them into equilibrium constants as concentrations, to be able to use this correction factor, RT to the delta N, to find the right answer.